Have you ever stopped to wonder how your social media feed knows exactly what to show you? Or how your bank keeps perfect track of every single dollar? Well, the magic behind all of that is something called a database management system, or DBMS for short. You can think of it as the ultimate digital librarian, the unsung hero that's busy organizing and protecting the massive amounts of data that make our modern world tick. All right, let's pull back the curtain and see how this all really works.
So here's our game plan for this explainer. We're going to start with the absolute basics. What even is a DBMS? Then we'll learn the language we use to talk to it, which is SQL. After that, we'll look at the different blueprints for actually building a database. Next up, we'll get into a super important process called normalization. Think of it as spring cleaning for your data. And finally, we'll wrap up by seeing how we protect our data fortress with things like keys and security.
Okay, first things first. What in the world is a DBMS? I want you to imagine trying to find one specific book in a massive library, but there's no catalog, no signs, no shelves. Just giant, messy piles of books everywhere. It would be total chaos, right? Well, that's what our digital world would look like without a DBMS. It's the software that steps in and brings order to that chaos, giving us a structured way to create, find, update, and manage all of our data.
Now, to tell our digital librarian what we want, we need to speak its language. And in the world of databases, that language is almost always SQL, which stands for Structured Query Language. But here's the thing, SQL is huge. So for today, we're going to focus on just one part of it, the Architect's Toolkit. These are the commands you use to actually build the structure of the database itself.
And that toolkit has a name. It's called Data Definition Language, or DDL. Now, the most important thing to get about DDL is that it never, ever touches the actual data. You know, the names, the numbers, the juicy details. Nope. DDL is all about building, changing, or completely demolishing the containers that hold the data. It's like you're building the filing cabinets and putting labels on the drawers, way before you ever put a single file inside.
And really, it all just boils down to these three fundamental commands. You create something new, you alter something that's already there, and you drop it to get rid of it completely. Seriously, with these three actions, you can manage the entire structure of any database. Let's take a quick look at each one. All right, here's the create command in action. With just this one line of code, we're basically telling the system, hey, build me a new table and call it employee. We're also laying out the columns it should have, one called ID for a number and another called name for text up to 30 characters long. We even assign the ID column to be the primary key. More on that in a bit. And boom, just like that, our digital filing cabinet is ready to go. But what happens when you realize you forgot something? Well, that's exactly what alter is for. Let's say we decide we also need to store a phone number for each employee. This command lets us go back to our existing employee table and add a brand new column called phone. It's that easy to make changes and let your database structure evolve over time. And finally, we come to the most powerful and, frankly, the most dangerous of the three, drop. This command doesn't just empty the table. Oh no, this is like taking the entire filing cabinet, files and all, and throwing it into a volcano. The structure, the data, everything, it's all gone, permanently. So yeah, this is one command you use with a whole lot of caution.
Okay, so we've seen the commands we use to build the individual parts of a database. But what's the overall game plan? What's the blueprint we should follow? That's where database models come into play. These are just different high-level designs for how data should be organized and how different pieces of information should relate to each other.
First up, we've got the hierarchical model. The easiest way to think about this is like a family tree. You've got a single root at the top, in this case the college, and it branches down into its children, like teachers and department. The key rule here is that every child can have only one parent. This setup is super fast for finding data if you follow the branches down, but it's also incredibly rigid. Its biggest flaw? It completely falls apart if you have a situation where a child needs more than one parent.
And to solve that exact one-parent problem, the network model was invented. It's less of a strict tree and more like a spider web. Now, as you can see here, a book can be connected to multiple authors. This was a huge leap forward because it could finally handle those complex many-to-many relationships. But all that new flexibility came at a cost. These systems were a whole lot more complex to manage. And that brings us to the reigning champion of database models, the relational model. This is the foundation for pretty much every modern database you've ever used. The idea behind it is just beautifully simple. All data is organized into tables, which are just grids of rows and columns. That's it. This approach is incredibly flexible, easy to wrap your head around, and unbelievably powerful.
So let's say we've picked a relational model, and we've built our tables. We're done, right? Well, not quite. Just because your data's in a table doesn't mean it's organized well. And that's where normalization comes in. It's basically the process of tidying up our database design to cut down on repeated information and make sure our data stays consistent and reliable.
So why do we even need to do this? Why does data get so messy in the first place? Well, it usually happens because when we first start designing a table, we tend to just lump all the related information together. And while that seems easy at first, it almost always creates big problems down the road, like having to repeat data over and over again.
Just look at this slide. This is a perfect example of messy, unnormalized data. Zero in on the row for the student Hari. See how in the subject and marks columns, there are multiple values just crammed into a single cell? That's what we call a repeating group, and it is a database's worst nightmare. It makes trying to search, sort, or update that information incredibly difficult. So, the very first step in cleaning this up is called first normal form, or 1NF. The rule here is super simple. Every single cell in your table has to hold a single atomic value, basically one piece of information per box, no more lists. So we take Hari's record and we break it out into 3 separate rows, one for each subject. See? It's already much cleaner. But we've just created a new problem. Now a bunch of his information is repeated, which brings us to the next step. Next up is second normal form, 2NF. This is all about getting rid of that redundancy we just created. I mean, look at our table now. The student's name, Hari, is repeated for every single class he's in. If he ever changes his name, you'd have to go and update it in 3 different places. That's just asking for trouble. So 2NF fixes this by splitting the table. We create one table just for students, where Hari's name is stored only once, and other tables for subjects and marks. Now, every piece of data has one logical home.
And finally, we get to the last stage of our cleanup, third normal form, 3NF. This step is about making our tables even more focused. The rule is to remove any information that isn't directly describing the main key of the table. In our example, the class name, like science, doesn't really describe the student's marks. It describes the class ID. So, 3NF tells us to move that into its own class table. What we're left with is a beautiful set of small, efficient tables, which is the goal of a well-designed database.
Okay, we have built our database and we've organized it beautifully. Now it's time to protect it. This last section is all about putting the locks on the doors. We're going to look at the tools we use to make sure our data stays accurate, consistent, and safe from anyone who shouldn't be seeing it.
And the absolute first line of defense is the primary key. This is a non-negotiable rule in the database world. Every table has to have one. A primary key is a column where every single row has a unique value. It's just like a student ID number at a school. No 2 students have the same one. This allows us to find one specific record with absolute certainty. Let's break this down with an example. In this student table, we actually have a few columns that could uniquely identify a student, right? The student ID would work, and so would the roll no. Any column that could be the unique key is called a candidate key. As the designer, our job is to pick just one of them to be the official primary key. In this case, we chose student ID. And the other candidates, the ones we could have picked but didn't, those are now called alternate keys.
So, these keys are all about enforcing something called data integrity, which is really just a fancy way of saying we're keeping our data trustworthy. There are 3 main rules here. First is entity integrity. It just means a primary key can never, ever be empty. Simple enough. Second is referential integrity. This makes sure the links between tables are valid. For example, you can't assign a student to a class that doesn't exist. And third is domain integrity. This just makes sure the data types are correct, like a marks column should only have numbers, not somebody's name. These rules are the guardians of our data quality.
And finally, let's talk about where the database actually lives. With a centralized database, all the data is stored in one single physical location. This is generally easier to manage and keep secure, but it's also a single point of failure. If that one server goes down, everything stops. The alternative is a decentralized or distributed database, which spreads the data across many different computers. This is way more reliable, but it's also more complex and expensive to set up.
And that's our tour of the world of database management systems. We've covered the language, the blueprints, the cleanup, and the security. So I'll leave you with one final question to think about, especially for those of you with an exam on the horizon. If you could only master one of these topics, which one do you think is the most critical to really truly understand? The different architectural models, the step-by-step process of normalization, or the fundamental concept of keys? Something to chew on.
Have you ever stopped to think about what's really happening when you send a quick message, stream a movie, or just browse a website? Honestly, it feels like magic, right? But it's not. It's all built on this massive, intricate system of hardware and rules. Our entire world pretty much runs on networks. And in this explainer, we're going to pull back that curtain and see exactly how it all works. So, where do we even begin? Well, we've got a roadmap. First up, we'll get down to basics and define what a network even is. Then, we'll follow a piece of data on its journey and see how it flows. After that, we'll look at the blueprints engineers use to design these things, explore how they scale up from just your room to the entire planet, and finally, we'll get our hands dirty with the actual physical hardware that makes it all happen.
All right, let's start at square one. Before we can talk about connecting the globe, we have to agree on what we're even talking about. So what is a network at its most fundamental level?
Okay, this is a really important distinction to get straight. Data communication is the action. It's the process, the verb. It's the act of sending information from point A to point B. But a computer network is the structure that lets that happen. It's the group of connected computers in the first place. You see, you really can't have one without the other.
So why even bother with all this complexity? Well, the perks are massive, right? We can share files and programs instantly, access our stuff from anywhere, and just communicate so easily. But there's a flip side. All that connection opens the door for security problems, makes it way easier for viruses to spread, and, yeah, things like software piracy. It's really a classic trade-off between power and risk. Now, for any of this to actually work, you need all 5 of these things. You've got the what, that's the message. You've got the who, the sender and the receiver, and you have the how, the media it travels on. But honestly, the most important piece here might just be the protocol. Think of it like a shared language. Without that set of rules that everyone agrees on, all you're sending back and forth is just digital noise.
Okay, so we've got our 5 essential ingredients. That brings up the next question, though. Once you send a message, how does it actually move? What are the digital rules of the road?
You know, data doesn't just flow in one standard way. There are actually 3 different modes. First, you have simplex. This is a one-way street. Think of a TV or radio broadcast. The signal only goes out. Then you've got half duplex. This is like a walkie-talkie. We can both talk, just not at the same time. And finally, there's full duplex, which is what we're all used to. It's like a phone call, where we can both talk and listen at the same time.
So the data has a direction, but what does it actually travel on? It's got to have a highway. And there are basically 2 types. You've got guided media, that's the wired physical stuff you can actually touch, like Ethernet cables or the fiber optic lines under our streets. And then there's unguided media, which is wireless. The data is just broadcast through the air using things like radio waves for Wi-Fi or microwaves for those long-distance connections.
So we know how data can flow and what it travels on. But how are all the computers themselves laid out? It's not just a big random mess. Every single network is built using a specific blueprint, and these are what we call architectures and topologies.
At the highest level, you've got 2 main design philosophies. Over on the left is the client-server model. Think of this like a library. There's one central server, the librarian, that manages all the books and resources, and then all the individual clients come and request things from it. On the right, you have peer-to-peer. This is more like a book club. Every computer is equal, and they all share information directly with each other.
So which one do you pick? Well, it really depends on what you need. As you can see here, that client-server model is super powerful and centralized, which is great for a big company. But it's also expensive and complicated to run. Peer-to-peer, on the other hand, is way cheaper and simpler, making it perfect for small groups. But you don't get that centralized control or security.
Now, if architecture is the big picture philosophy, then topology is the nitty-gritty physical layout. It's the literal map of how everything is plugged together, the arrangement of the computers, the cables, and all the other devices. It's basically the city plan for your network.
And here are a few of the most common plans. In a star network, everything connects to one central point. It's easy to manage, but if that central hub goes down, the whole network is out. With a bus network, everybody just plugs into one main cable. It's cheap, but it's risky. One little break in that cable and everyone's offline. And then there's a ring, where the data just goes around in a circle, passed from one computer to the next.
So we've got our blueprint, our topology, but how big is this city that we're building? Well, the scale of a network is one of its most important features, and that's what we're going to dive into next.
It all starts small, with a LAN, a local area network. That's your home Wi-Fi or your office network. Now, if you link a bunch of those LANs together across a city, you get a MAN, a metropolitan area network. And when you connect those networks across countries and continents, that's when you get a WAN, a wide area network. The internet itself is just the biggest WAN in the world.
And you can see there's a really fundamental trade-off between LANs and WANs. Because the distance is so short, LANs are incredibly fast, pretty cheap, and super reliable. But the second you start stretching that connection across a country with a WAN, you have to sacrifice some of that speed and reliability to get that incredible reach. It's this constant balancing act.
All right, let's quickly clear up 3 words that people mix up all the time. The internet is the big one, the public network that anyone can get on. An intranet is a totally private internal network for just one company, like their employee portal. And an extranet is kind of a middle ground, where a company lets specific outsiders in, like their suppliers or business partners. Really, it all just comes down to who's allowed in the door.
Okay, we've talked about concepts, rules, blueprints, all the abstract stuff. But what about the actual physical things? For our last section, let's get our hands dirty and look at the hardware, the nuts and bolts that make any of this possible.
Let's run through the major players. First, every single device needs a NIC, a network interface card. It's your ticket to get on the network. A modem is a translator. It turns digital computer signals into analog ones for things like phone or cable lines. A hub is the simplest connector. It's like a town crier, just shouting any data it gets to every single device connected to it. A switch is way smarter. It's like a mail carrier, looking at the specific address on the data and delivering it only to the computer that's supposed to get it. A bridge connects 2 similar networks together. And finally, a gateway is the ultimate diplomat, letting 2 completely different kinds of networks talk to each other.
So here's the main takeaway. What feels like this seamless, instant communication is actually built on all these different layers of complexity. It's this carefully designed system where the physical hardware, the network layout, and the rules of communication all have to work together perfectly.
And that brings us to one last thing to think about. We've just broken down the building blocks that created the connected world we have right now. So, what happens when those building blocks change? When our wireless media gets even faster and our network architectures get even smarter, how is that going to change the very fabric of how we live and communicate? Something to chew on. Thanks for watching.
You know when you fill out a form online, hit submit, and just wonder what happens? Where does all that info actually go? Well, today we're going to pull back the curtain and follow that data on its entire journey, from the code you can see in your browser all the way to the powerful databases that are the hidden engines of the web. So here's our game plan for this trip. We're going to kick things off with JavaScript, which is basically the brains of your browser. Then we'll see how code can make decisions and do things over and over again. After that, it's the big showdown, client versus server. We'll then get to know the server-side powerhouse, PHP, and finally, we'll uncover the secret to getting everything talking to a database. All right, first up, JavaScript. Look, if HTML is the skeleton of a website and CSS is the skin and clothes, then you got to think of JavaScript as the brain and the muscles. It's the part that actually makes a page do things, bringing it to life and making it interactive. Now, the most important phrase to remember here is client-side. All that means is that the JavaScript code is downloaded and runs directly on your computer, inside your web browser. This is why it's so fast. Think about when you're typing in a form and it immediately tells you, hey, that's not a valid email. That's JavaScript working right there on your machine, giving you instant feedback. Okay, don't get intimidated by the code on the screen. It's actually pretty simple. Let's just walk through it. First, you see the word var. That's just us creating a couple of little boxes or variables to hold some numbers. Next, we define a function. Think of it as a reusable recipe. This recipe's only job is to add 2 numbers. The very last line is us telling the browser, okay, run that recipe now. So, what is a variable, really? Honestly, the easiest way to picture it is just a labeled box where you can store some information. But here's the crucial part. Where you create that box matters a whole lot. If you make it inside a function, it's local, meaning only that function can see it. If you make it outside of any function, it's global, and your entire script can see and use it. And the stuff you put in those variable boxes comes in different flavors. You've got your primitive types, which are the real basics. A string is just text, a number is, well, a number, and a Boolean is the simplest of all. It's just true or false. That's it. Then you have the more complex types for when you need to group a bunch of data together. Operators? Think of these as the verbs in your code. They're the action words. You've got your standard math operators, right? Plus, minus, multiply, divide. Then you have comparison operators to check if something is equal to or greater than something else. Logical operators let you chain conditions together. But maybe the most important one is that single equals sign. It doesn't ask if things are equal. It makes them equal. It assigns the value. All right, so we have boxes to hold our data and verbs to act on it. But how do we make our code smart? How do we get it to repeat things, or better yet, react to what a user is doing? Well, that's exactly where loops and events come into play. When it comes to repeating actions, you've got three main tools. A for loop is your best friend when you know precisely how many times you need to do something, like count to 10. A while loop is for when you don't know. It just keeps on going until a specific condition is finally met. And the do while loop? It's almost the same, but it guarantees your code will run at least one time, no matter what. Now, this is how a web page really comes alive. An event is literally anything you do on the page, clicking a button, hovering over an image, pressing a key on your keyboard, and JavaScript is basically sitting there just listening for these things to happen. So you can set up an on-click event that says, hey, the very moment someone clicks this button, pop up an alert that says, hello world. Okay, what we're about to cover next is a total game changer for understanding how the web really works. Everything we've talked about so far with JavaScript happens on the client. That's your computer. But that's only half the story. It's time for the big showdown, client side versus server side. So on the client side, you've got JavaScript running in your browser. It's fast, it handles all the cool user interface stuff. But here is the number one most important rule to remember. It absolutely cannot connect to a database. And for good reason. You wouldn't want code on some random person's computer to have direct access to your company's data. No way. For that kind of heavy lifting, you need a language running on your web server, like PHP. It can securely talk to the database. This diagram here shows you the whole dance. It starts with you in your browser. You send out what's called an HTTP request to a web server. Think of it like a text message asking for a specific page. The server gets that message, runs a PHP script, which then has a little chat with the database to get or save info. Finally, the server packages everything up into a nice HTML page and sends it right back to your browser as the response. That's the whole loop. So let's zoom in on that server-side engine. Now, there are a bunch of languages you can use on the server, but a true classic and a fantastic one to learn is PHP. It is the invisible workhorse that powers a massive chunk of the internet. So why is it so popular? Well, for starters, it's open source, which means it is totally free. Finding a place to host your PHP website is super cheap and easy. It doesn't care if you're using Windows, a Mac, or Linux. It just works everywhere. And on top of all that, it has tons of free libraries, which is just pre-written code you can use so you don't have to build everything from scratch. Okay, if you're coming from the world of JavaScript, there are two huge rules you have to burn into your memory for PHP. First, all of your code must live inside these special PHP tags. Second, and this is the one that trips everyone up at first, every single variable has to start with a $sign. It feels a little weird, but you just have to remember it. All right, let's get to the main event. This is what we've been building towards. We've got our user interface on the client side, and we've got our powerful engine on the server side. Now, it's time to build the final bridge and connect our PHP code to a MySQL database. This right here is the blueprint for making almost any dynamic web application. There are just 4 essential steps. And you'll want to pay close attention because the source material for this explainer specifically calls this out as a really high-value topic that shows up on exams a lot. Step 1 is simple. You have to establish a connection. It's like making a phone call to the database. You use a built-in PHP function and just give it the 4 pieces of info it needs: the server's address, a username, a password, and the name of the database you're trying to call. Once you're connected, you can start sending commands. The language you use to talk to a database is called SQL. So to add new data, like when a new user signs up, you build an insert command out of text, then you just hand that command over to another PHP function that sends it off to the database. And now for the really cool part, getting data out of the database. You use a select query in SQL to ask for the data you want. Then, to get it on the screen, you use this awesome 2-part combo. a while loop that keeps running as long as there are results, and inside it, a function that grabs one row of data at a time for you to display. And I want to leave you with this last critical tip because it's so important. This entire four-step process is a classic big-ticket exam question. And the key to getting all the marks isn't just knowing the steps, it's getting the syntax perfect. You have to double-check every single $sign for your variables and make sure your quotation marks are correct. That's where people lose easy points. So there we have it. We have made the complete journey from a simple script in your browser to a server-side engine all the way into a database and back again. You now understand the fundamental architecture of almost every dynamic website you use every day, which really only leaves one question. Now that you know how to connect the front end to the back end, what would you build first?
Hey everyone, and welcome. Today we're diving into one of the most important topics for your NEB board exams, C programming. Seriously, this is the stuff that high-yield 8-mark questions are made of. And by the end of this, we're going to build the master program that ties all the key concepts together.
So let's start with a problem. Picture this. You're a teacher, and you need to store the roll number, the name, and the marks for an entire class of 100 students. How on earth do you manage all of that related info in a single program without it becoming a total nightmare? Well, that's the exact question we're going to answer today.
And here's our game plan. We're going to start with the essential building blocks, things like arrays and functions. Then we'll level up to the most powerful tool in our toolbox, structures. And by the end, we'll combine everything to build a complete student record system right from scratch.
All right, first things first. We need a way to handle a lot of data all at once. I mean, if we have 100 students, we can't just go and create 100 separate variables, right? That would be crazy. We need a much smarter tool for the job.
And that tool is the array. Just think of an array as a big container. Instead of having a variable called marks1, then marks2, then marks3, you just have one big container called marks, and it has a bunch of numbered slots to hold all the student marks. Now here's the one big rule you got to remember. All the values inside that container have to be of the exact same data type.
And actually putting this into code, it's surprisingly simple. You can see here, we declare an integer array, int a5, which basically says, hey computer, give me 5 slots for integers. Then we use a for loop, which is a total workhorse in C, to cycle through each one of those slots and fill it up with a number the user types in. It's clean, it's efficient, and it's really powerful.
But wait a minute, students have names, right? And names aren't numbers, they're text, or what we call strings in C. The good news is, C gives us a whole library of ready-made tools for messing with strings. All you have to do is include the string.h header file, and trust me, you're going to want to pay close attention to functions like strcmp and strcpy. They're going to be absolutely essential in a little bit.
Okay, so we've got our data stored away nicely in arrays. That's great. But raw data sitting there isn't all that useful. We need to start organizing our code so we can actually do things with it. And we need to organize the data itself, maybe by, say, sorting it.
This is where functions come into play. A function is really just a chunk of code that you give a name to. Why? So you can use it over and over again without having to rewrite it every single time. It keeps your main program looking clean and organized. Instead of one gigantic, messy block of code, you have these neat, tidy little pieces that each do one specific job.
Now, one of the most common jobs you'll do is sorting data. The bubble sort is a total classic, and it's a huge favorite on exams. The logic is actually pretty simple. You just use 2 loops, one inside the other. The outer loop grabs an element, and the inner loop compares it to all the others. If they're in the wrong order, you just swap them. And you just keep doing that over and over until the whole list is perfectly sorted.
Okay, now lean in because this is a golden tip for your exam. If you need to switch from sorting in ascending order, smallest to largest, to descending order, you don't have to rewrite a single thing. You just change one character. That's it. You flip the greater than sign in your if condition to a less than sign. A tiny change for a completely opposite result. Remember that one.
So far, so good. We can handle a list of numbers, and we can handle a list of names. But that's not our real-world problem, is it? A student record is a mix of different data types all bundled together. And for that, we need a much more powerful tool.
And here it is, the big challenge. An array can hold 100 integers, sure, or 100 strings. But it can't hold an integer, a string, and another integer all together in a single slot. So how do we bundle all those different pieces of information for a single student into one neat package?
The answer, my friends, is a structure. This is basically C's superpower for organizing data. A structure lets you literally invent your own data type. You get to define a template, a blueprint, that groups an integer, a character array, a float, whatever you need, all under a single name.
Let's take a look at the actual code. What we're doing here is creating a blueprint called struct student. And inside, we're laying out the rules. We're saying that every single student from now on will have an integer for their roll number, a character array for their name, and another integer for their marks. Now, we haven't actually created any students yet. We've just designed the perfect student cookie cutter.
And now, for the magic. This is where it all comes together. We can combine our two amazing tools. We can declare an array, but not an array of integers or characters, an array of our brand new, custom-made data type, struct student. This one single line of code creates space for 10 complete student records, and each of those records has a spot for a roll number, a name, and marks. This is how we solved that original problem.
All right, we've gathered all our individual pieces. We have arrays, functions, and now these powerful structures. Let's put them all together and build the kind of complex, awesome program you're definitely going to be asked to write in your NAB exam.
This is it, the 8-mark heavy hitter. This is what separates the good scores from the great ones. We're taking everything we've learned and using it to sort an entire array of student records. Maybe we want to sort them alphabetically by name or in ascending order of their marks. Either way, this requires some really careful data handling.
So how do you actually swap two of these student records when you're sorting? This right here is the most crucial part. You can't just swap the names or just swap the marks. That's a disaster. You have to swap the entire student record as one single block. As you can see here, you need a temporary variable that is also a struct type so it can hold one entire record while you do the swap. The whole block has to move together. And hey, don't just take my word for it. This is without a doubt the #1 trap that students fall into on the exam. They get the sorting logic right, but then they only swap one piece of the data, like the name, and that completely corrupts their records. Suddenly, student A's marks are attached to student B's name. It's a mess. You have to swap the whole thing. So let's just burn this into our memory right now. It's 4 simple steps. Step 1, create a temporary variable of the exact same structure type. Step 2, copy the entire first student record into that temp variable. Step 3, copy the second record into the first one's original spot. And finally, step 4, copy that record you saved in temp into the second one's spot. It's the same 3-step swap we all know, but you're moving entire blocks of data.
Okay, one final critical tip. If you are comparing or copying the strings inside the structure, like when you're trying to sort by name, you cannot, I repeat, you cannot use the double equal sign or the single equal sign. It won't work. You absolutely must use the string library functions, strcmp for comparing the names and strcpy for copying them. This is another really common place where people lose easy marks.
So there you have it, the complete blueprint. We've gone from a basic array all the way to the all-powerful structure, and you now know the critical logic for sorting them without falling into the common traps. The only question left is, can you put it all together? Can you now write a full program to manage and sort that data? After what we just covered, you absolutely can.
All right, NEB scholars, welcome. Today, we are tackling a huge topic. And really, it's not just another chapter in your textbook. It's the entire modern blueprint for how programming gets done. We're talking about object-oriented programming, or OOP. And let's be real. This is a guaranteed 5 to 8 mark question on your exam. So getting this down is, well, it's not optional. Okay, let's get into it. So here's our game plan. First, we'll get into what OOP actually is. Then we'll look at the 4 huge pillars that hold it all up. After that, we're going to put it head-to-head with the older way of doing things, procedural programming. And finally, we'll map out all the different types of inheritance. This is your roadmap to absolutely crushing this chapter. So what's the big deal with OOP? Well, it's a completely different way of thinking. Instead of just writing a long to-do list of commands for the computer, OOP makes us focus on what's truly important, the data itself. It's all about creating models of real-world things right inside our code. Now, pay attention to this slide, because this is the definition your examiners are looking for. There are 3 key phrases here you have to remember. First, it focuses on data, not procedure. Second, it uses a bottom-up approach, which means we build small, independent pieces first and then put them together. And third, a massive feature is inheritance, which is all about reusing code. If you get those keywords in your answer, you're golden. But, no tool is perfect for every single job. OOP is an absolute powerhouse for managing giant, complex software. Think about things like Facebook or even your computer's operating system. The security you get from data hiding and the ability to reuse code are massive wins. But is it the right tool for a tiny, simple script? Probably not. It can be overkill, and it definitely requires you to wrap your head around a totally new way of thinking. Okay, let's get to the heart of it. Everything, and I mean everything in OOP stands on 4 giant pillars. Understanding these isn't just a good idea, it's absolutely essential. These are the fundamental building blocks that make OOPs so powerful, and they're the foundation of pretty much all the modern software you use every single day. First up, we have the class. The best way to think about a class is to imagine an architect's blueprint for a house. Now, the blueprint itself isn't a house, right? You can't live in the drawing. It's just the plan. That's exactly what a class is. It's a template for something, like a user on an app or a car in a game. And the most important thing to remember is this: the class itself is just the plan, so it doesn't take up any memory. And here's a perfect example. On the left, you see the class called vehicle. That's our blueprint. It lays out the rules. Every vehicle must have a model, a color, and it should be able to start and stop. Then on the right, you see the objects. These are the actual cars, the Mustang, the Civic, the Tesla. They're real things built using that blueprint, and each one has its own specific details. Which brings us perfectly to the object. So if the class is the blueprint for a user, then an object is your actual profile. It's a real living, breathing instance of that class. This is the part that actually gives life to the blueprint. And crucially, this is what takes up space in your computer's memory when a program is running. Our second pillar is encapsulation. The name gives it away, really. It's like taking your data and the functions that can change that data and sealing them together inside a protective capsule. This is the secret sauce for security in OOP. It's a concept called data hiding, and it's basically why one app on your phone can't just reach in and steal data from another one. Now look at this diagram here. See how the private data is tucked away safely inside the capsule? The only way anything from the outside can touch that data is by going through the public functions. Those functions act like a security guard at a gate. This is awesome because it stops other parts of the program from accidentally or maliciously messing up your important information. Pillar number 3 is data abstraction. Now, this sounds really technical, but I promise you, you use it every single day. Think about driving a car. You use the steering wheel, the brake, the accelerator. You don't need to be a mechanic and understand how the engine works, right? Or when you tap an app on your phone, you don't need to see the millions of lines of code running behind it. That's abstraction, just showing the simple, essential controls and hiding all the complicated stuff in the background. And you can see that idea right here. Behind the scenes, a class could be incredibly complex, with tons of data and functions. But with abstraction, we just hide all of that messy detail. We only show the simple interface that someone needs to use it. This makes our programs so much easier to work with and way less likely to break. And now for our fourth and, you could argue, the most powerful pillar of all, inheritance. This is the absolute core of code reusability in OOP. And it works just like it sounds. A child inherits traits from a parent, right? Well, in programming, a new class can inherit all the features and behaviors from another existing class. So, for example, you could have a premium user class that inherits everything from a basic user class and then just add a couple of new special features. So let's see how this actually works. In this diagram, the new class is the child, or what we call the derived class. It automatically gets everything from the existing class, which is the parent, or base class. So why is this so incredible? Because you don't have to write all that code over again. It saves a ridiculous amount of time and effort, and it means fewer bugs to fix. Okay, our last big concept here is polymorphism. Now, don't let the name scare you. It's just 2 Greek words smashed together. Poly means many, and morph means form, so it literally just means many forms. In programming, it's this amazing ability for one thing, like a function name, to have many different behaviors depending on what you're doing with it. This picture makes it super clear. Imagine you have a function in a drawing program called draw. Now, if you give that function a circle object, what does it do? It draws a circle. But if you give that same draw function a square object, it draws a square. See? One name, draw, but it can take on many forms. That's polymorphism. And it makes code incredibly flexible and powerful. Okay, everyone, lean in for this one. This next part is VVI, very, very important. The question asking you to compare object-oriented and procedural programming is one of the most common, almost guaranteed questions on the NEB exam. You absolutely have to know this. Let's break this chart down. OOP uses a bottom-up approach, building with small objects, while POP is top-down, starting with the main procedure. The main focus for OOP is data, organized into classes. For POP, it's all about the procedure or the functions. The biggest difference? OOP has incredible features like inheritance that make reusing code super easy. POP? It just doesn't have a built-in way to do that. And remember the examples. Modern languages like C++ and Java are OOP, while older ones like C and Fortran are POP.
Now, I've got a little exam hack for you to lock in those differences. Just remember the acronym BDFFRE. That stands for Bottom-Up, Data, Features, Functions, Reusability, and Examples. Seriously, just use that acronym as a checklist in your exam, and you'll hit every single important point for this question. It's a lifesaver. We are in the final stretch, I promise. We know what inheritance is, but it actually comes in a few different flavors. Now, for this section, you have to listen carefully. To get full marks on this question, drawing the block diagrams for each type is mandatory. You must draw them.
So on the left here, we've got the simplest kind, single inheritance. It's exactly what it sounds like. One child class inherits from one parent class. Easy. On the right is something your notes call multi-inheritance. This is where a single child class can inherit from multiple parent classes at the same time, basically grabbing features from both of them.
Next up, we have hierarchical inheritance. Think of it like a family tree, where one parent has lots of different children. And finally, there's multi-level inheritance. This one is like a chain reaction. Class C inherits from Class B, which in turn inherits from Class A. It's like a grandparent-parent-child relationship. Now, just a quick heads up for your exam, that concept of one child having many parents is often called multiple inheritance in the wider world of computer science. If your textbook calls it multi-inheritance, stick with that term. Just make sure your diagrams and terms match what you've been taught. Okay, let's do a super fast recap of everything you need to know for the exam. Ready? OOP is bottom-up and all about data. You have to master the 4 pillars: encapsulation, abstraction, inheritance, and polymorphism. The OOP versus POP question is pretty much guaranteed, so use BDFRE. Remember to always draw the diagrams for the inheritance types. And the 2 superstar features of OOP are data hiding and code reusability. Got it? And that's it. We have gone through the entire blueprint for object-oriented programming. You now have the tools, you have the concepts. So I have one last question for you. Now that you understand the power of classes and objects and inheritance, what kind of complex, real-world system would you want to build first? A video game? A social network? A banking app? Let your imagination run with it. Good luck on your exams. You ever wonder how the apps on your phone go from just a random idea to, well, a full-blown program? It's definitely not magic. It's actually a really carefully planned journey. And today, we're going to pull back the curtain and show you exactly how it's done. I mean, it's a great question, right? How do developers take a simple concept, like, hey, what if we made a way to share photos, and turn it into something massive like Instagram, with all the filters, the stories, the whole shebang? Well, it all comes down to having a solid blueprint. And that blueprint, it's called the Software Development Lifecycle, or you'll hear it called the SDLC for short. The best way to think of it is like the ultimate recipe for building software. It's a structured plan that guides a project from the very beginning to the very end, making sure nothing, and I mean nothing, gets missed. Okay, so here's our game plan for today. We're going to start with the big picture, the SDLC blueprint. Then we'll walk through all the different phases, step by step. After that, we'll meet a key player, the system analyst. We'll even check out different ways to build a project. And finally, talk about what makes software, well, good. Let's get right into it. All right, first up, the blueprint. Before we dive into the nitty-gritty, let's just get that high-level bird's-eye view of what this whole life cycle is all about. Okay, take a look at this. The most important thing to notice right away is that the SDLC isn't a straight line. It doesn't just end. It's a continuous cycle, a loop. You go through all these phases, from the initial study all the way to maintenance, and that last step, the review, it often feeds right back into the beginning to kick off the next version. It's all about constant improvement. All right, now that we've seen the big map, let's zoom in. We're going to walk through this whole journey, one phase at a time, starting right at the very beginning.
So everything kicks off with phase 1, the system study. Now, before anyone even thinks about writing a line of code, you have to ask the most critical question of all. Is this idea even possible? Is it worth doing? This is where the team dives into what's called a feasibility study. And trust me, this isn't just a simple thumbs up or thumbs down. A feasibility study looks at the idea from every possible angle. We're asking things like, do we even have the technology for this? That's your technical feasibility. Does it make financial sense? That's economical. You even have to consider legal stuff and how it fits in socially. Seriously, this step is so crucial. It stops companies from pouring tons of money into an idea that was basically doomed from the start. Okay, so once the project gets the green light, we move on to phase 2, system analysis. The goal here is simple but super important. Figure out what the user actually needs. What does this software need to do? So the team goes out and gathers all the requirements from the people who will actually use it, through interviews, surveys, maybe even just watching them work, to build a really clear picture of what the final product should be. So you've got all those requirements. Now what? Well, now it's time for system design. This is where the technical blueprint gets drawn up. You take the what we need from the analysis phase and you translate it into the how we're going to build it. And this is where things like algorithms and flowcharts become super important for mapping out the entire system's logic. And a flowchart is a perfect example of one of these design tools. It's basically a visual map of how the program is going to think. See those ovals? Those are your start and end points. The slanted rectangles, the parallelograms, they're for inputs and outputs, like when a user types something. The regular rectangles are for actual processing steps. And the diamonds? Those are your decision points, your if this then that moments. It's pretty much a universal language that programmers can use to understand the plan. Next up, phase 4, system development. This is the part that feels like magic to most people. The programmers take all those design documents, those flowcharts we just talked about, and they get to work writing the actual code. They're turning that blueprint into a real, tangible thing. But you can't just write a bunch of code and hope for the best, right? Of course not. That brings us to a super important phase, system testing. And hey, lean in for this one, because this is a classic exam question. There are 2 main types you need to know. First, you've got black box testing. Think of it like you're a user. You can't see the code inside, you're just clicking buttons to see if they work. Then there's white box testing. This is the opposite. The tester is like a mechanic looking under the hood, checking the code itself to make sure it's efficient and built correctly. Okay, the last 3 phases really wrap everything up and bring it home. Phase 6, system implementation, that's the big launch day, getting the software out into the wild. Phase 7 is system maintenance, which is all the ongoing work, fixing bugs, helping users, adding new features. And finally, Phase 8, system review. This is where the team looks back at the whole project and asks, how'd we do, and what can we do better next time? So, we've walked through the entire process, all 8 phases. But who's actually in charge of guiding this whole thing? Let's talk about the key player in this journey. That person is the system analyst. You can think of them as the crucial bridge that connects the world of the users with the world of the programmers. Their whole job is to figure out what the system needs to do. The software engineer, their job is to figure out how to actually build it. It's a great way to remember it. The analyst defines the problem, and the engineer builds the solution. Okay, so those 8 phases we talked about, they're pretty much always there. But the way you move through them, well, that can be totally different depending on the project. Let's look at the different roadmaps or models that a team can choose from. First up is the old school classic, the waterfall model, and it works exactly like it sounds. It's simple, it's linear, and it is rigid. You have to finish phase 1 completely before you can even start phase 2, and so on down the line. It's just like a real waterfall. Once the water goes over the edge, there's no going back up. This model is really only good for simple projects where you know exactly what you need from day 1, like say building a basic calculator app. But what happens when you're not 100% sure what the user wants? Well, for that, there's the prototype model. The idea here is you build a quick and dirty version of the software, a prototype, and you get it in front of the user right away. Think about designing a new video game. You wouldn't build the whole game. You'd build one level, let people play it, get their feedback, and then you just refine it over and over again in a loop. It's all about getting that user feedback early and often. Now, for the really big, really complex projects, you've got the spiral model. Each loop you see in this spiral is like its own mini project. It tackles one piece of the system at a time, and it always starts by looking at the risks. This whole model is designed to handle uncertainty, which makes it perfect for those massive projects where the stakes are incredibly high. We're talking about things like building the control software for a brand new airplane. And finally, we have to talk about the modern champion of development, the Agile model. Agile is all about two things: speed and flexibility. The work gets broken down into these small, manageable chunks called sprints. Just think about how an app like Spotify gets updated. You don't get one giant update a year, right? You get small, frequent new features. Every one of those little updates is basically a sprint. There's a reason this is the go-to model for most companies today. So we've covered the phases, we've covered the different models you can use. But what's the end goal of all this? What are we actually trying to achieve at the end of this whole journey?
The goal, plain and simple, is to create quality software. And quality means a few key things. It's got to be error-free, that's a given. But it also has to be easy for people to use and, this is important, easy for other developers to update down the road. It should be flexible, able to run on different systems, and, crucially, it has to be efficient. It shouldn't be a resource hog that slows down your whole computer. Following a good SDLC process is what helps you hit all of these targets.
So, at the end of the day, the SDLC is so much more than just a series of steps on a chart. It's the framework that brings order to the beautiful chaos of creating software. It's what turns a messy brainstorm into a polished, useful, and reliable app. So the real question to leave you with is this: when your next big idea strikes, which path are you going to take to bring it to life? The rigid waterfall, the feedback-focused prototype, or the fast and flexible agile?
Hey everyone, today we're tackling some of the biggest topics in tech right now. And listen, this isn't just about what's cool and futuristic. This stuff is absolutely crucial for your NMB exam. So if you're looking to really nail those questions, stick around. You're in exactly the right spot. Let's get into it.
Okay, here's our game plan. We're going to start with the cloud, kind of the bedrock of everything. Then we'll get into the brains of the operation, artificial intelligence. After that, we'll see how it all powers digital money and services, and how everything gets connected with IoT. All of that creates, you guessed it, big data. And definitely stick around till the end, because I've got some killer exam hacks that you are not going to want to miss.
So let's kick things off with Section 1, the world in the cloud. It's funny, you probably use this technology dozens of times a day without even thinking about it. It's like the invisible force holding up our entire digital world.
Okay, so what in the world is cloud computing? Well, at its core, it's basically a giant network of super powerful computers. We call them servers, that you can tap into from anywhere as long as you've got internet. So, instead of that photo you just took living only on your phone, you're actually saving it on a computer owned by someone like Google or Apple. The magic part? Now you can pull up that same photo on your laptop, your tablet, pretty much any device, anywhere. Of course, there's always a trade-off, right? On the one hand, the advantages are incredible. I mean, accessing your files from literally anywhere, that's a game changer. But there's always a but. The big downside? You're completely dependent on an internet connection. And you have to think about security. You're basically handing your data over to another company and trusting them to keep it safe. All right, now this is where it gets interesting. The cloud isn't just some big single thing. It actually comes in different flavors, or layers. The best way to think about it is like we're building a pyramid, starting from the very bottom. So, at the very base of our pyramid, we have what's called IaaS. That stands for Infrastructure as a Service. This is the absolute foundation. Think of it like renting a plot of digital land and a pile of bricks. You get the raw materials, the servers, the storage, all the basic hardware, and you can build whatever you want on top of it. Okay, moving up one level, we get to PaaS, or Platform as a Service. Now, if IaaS was just the land and bricks, PaaS is like a pre-built workshop on that land. It's got all the tools you need already set up, things like operating systems and databases. So developers can just walk in and start building their apps without having to worry about setting up the workshop itself. And finally, sitting at the very top of our pyramid is SaaS, Software as a Service. This is the part you and I use all the time. It's the finished product. We're talking about things like Google Docs or Netflix or Spotify. It's software that's just ready to go. You don't build it, you don't manage the workshop, you just open it up and use it. Simple as that. Okay, so we've got this amazing cloud infrastructure, right? But infrastructure alone is just, well, it's just plumbing and wires. What makes it truly powerful is when you add a brain to it. And that brings us to our next huge topic, artificial intelligence. So what is artificial intelligence anyway?
In a nutshell, it's all about making computers do things that usually require a human brain. We're talking about the ability to see and understand what's around them, to get what we're saying in plain English, to learn from mistakes, and to actually make decisions. It's really about teaching machines how to think.
And AI isn't just some sci-fi concept anymore. It's everywhere. And it's not just one thing either. It's a whole bunch of different tools and applications that are changing, well, pretty much everything. Let's take a look at 6 key ways it's already in action.
Seriously, think about it. That perfect show Netflix just suggested for you? AI. When you ask Alexa or Siri about the weather, you're talking to AI. It's helping doctors spot diseases earlier in hospitals. It's the ridiculously smart opponent in games like PUBG that seems to know your every move. It's what's powering self-driving cars, and it's even running factory floors more efficiently than ever before. It's everywhere.
So we've got the cloud and we've got AI. Now, when you put those two together, they completely change the game for how we buy things, sell things, and even how we interact with the government. That leads us right into digital transactions.
This chart breaks it down really nicely. On one side, you've got e-commerce. That's just buying and selling stuff online. You have business to business, or B2B. Then there's B2C, business to consumer, which is like you buying something from Amazon. And C2C, consumer to consumer. That's like selling your old phone online. Then on the other side, we have e-governance. That's just a fancy way of saying the government using tech. Think about paying your taxes online. That's government to business. Or renewing your driver's license from your couch. That's government to citizen. See? Pretty straightforward.
Okay, check this out. We've got the cloud infrastructure. We've got the AI brains. What happens when we start putting those brains and that connectivity into, well, everything? That, my friends, is the Internet of Things, or IoT.
So what is IoT? It's this massive, growing web of everyday physical things. We're talking your smartwatch, your TV, even your refrigerator that have been given a little bit of digital magic. They're packed with sensors and software, and the key part is they're all connected to the internet, constantly talking to each other and sharing data.
And yeah, you guessed it, just like with the cloud, there are two sides to this coin. The upside is amazing, right? A world where everything is smarter, more convenient, and more efficient. But the downside, well, it can be pretty scary. We're talking about major security risks. What if someone hacks your smart home? It's also super expensive to get all this stuff set up. And here's a wild thought. One tiny software bug could mess up all the connected devices in a system. That's a huge risk. So let's put it all together. We have billions of IoT devices all talking to each other, running on AI, all hosted on the cloud. What's the one thing all of this creates? An unbelievable, mind-blowing amount of data. And that brings us to our last major concept. Big data.
Now, when we say big data, we don't just mean a lot of data. We're talking about a flood of information that's so massive, so complex, and growing so ridiculously fast, exponentially fast, that your normal computer or regular software just can't keep up. It would just completely crash.
Okay, and to really wrap your head around big data, and trust me, this is super important for the exam, you need to know what defines it. We call them the V's of big data, and there are 6 of them you absolutely have to know. Let's run through them real quick. First, volume. That's just the sheer size of it all. It's enormous. Then velocity, how fast it's all coming at us, like a fire hose. Variety, it's not just neat rows and columns. It's everything from photos and videos to tweets. Veracity, this is a big one. Is the data even accurate? Can we trust it? Value, what's the point of all this data if we can't get something useful out of it? And finally, variability. The data is always changing and can be really inconsistent.
Woo! Okay, we have covered a ton of ground. But now it's time for the moment you've been waiting for. Let's boil all of this down into the cheat codes you need to absolutely smash this section on your NEB exam.
All right, get ready to screenshot this or write it down. For the cloud, just remember, IaaS is infrastructure, the raw parts. PaaS is the platform, the workshop. And SaaS is the software, the finished product. Easy. For the AI applications, remember this little acronym, RVHGAI. That's for recommendation, virtual assistant, healthcare, games, automobiles, and industries. And for big data, you just have to burn those 6 V's into your brain. Get these down, and you'll be golden.
So, I want to leave you with a big question to chew on. We've talked about the cloud, AI, IoT, and big data. If you had to bet on just one of these, which one do you think is going to change our world the most in the next decade? There's no easy answer, but it's definitely something to think about. Thanks so much for tuning in.